Good afternoon, everyone. My name is Yifan, and the topic I'm going to present today is the X-Bond qubit. But before I get into the technical details of what the X-Bond qubit is, let me first give you guys a historical overview of how the X-Bond qubit came into being. The X-Bond qubit is a type of superconducting qubit. It is mainly based on Josephson junctions, which were proposed by British physicist Brian David Josephson in 1962. Since then, structures based on Josephson junctions were exploited by a number of researchers, including Dr. Deverett and Dr. Borchet, in as early as the 1990s. However, superconducting qubits were not practical until 2007, when Yale scientists proposed a structure called the transbond. And since then, improvements to the transbond became a very hot research topic. So what exactly is the problem here? Quantum coherence in superconducting circuits can be very delicate. There are a number of factors that could affect quantum coherence. So firstly, material defects. The qubit could be easily coupled to the defects on the material and would thus result in decoherence. And second, electron system excitations. And this is also why superconducting qubits need to be placed in ultra-low temperature. It needs to be as low as about 30 millikelvin. And thirdly, radioactive coupling to external wiring, and this is why the structure of the transbond is very important. Other factors are also very important, such as connectivity and fast control. So this is why, and this is basically the motivation of creating the X-bond, which is basically an improvement to the classical transbond. So the X-bond was proposed by a group of UCSB researchers led by Professor John M. Martinez in 2013. It is a fully planar superconducting qubit, which is very suitable for scaling up and manufacturing. It is also frequency tunable, allowing Control Z gate. And finally, it has a relaxation time T1 of about 40 microseconds, exceeding gate times by 3 orders of magnitude. So now let's take a closer look at the structure of the device. So Figure A is an optical micrograph of the planar X-bond qubit formed by aluminum superconducting film and sapphire substrate. It has 4 arms, and each arm has a different function. On the top, you can see a readout line and readout resonator. It is basically used for reading out the qubit. On the left, you can see an XY control, and this line is used to excite the qubit. The right is a quantum resonator, which is used to mediate coupling with other qubits, and on the bottom is a Z control. The Z control is used to the qubit frequency. In the middle, there is a cross. The cross is a qubit capacitor, which connects at the bottom to the tunable Josephson junction, formed by the rectangular ring-shaped squid. The rectangular ring is intersected by 2 identically sized aluminum tunnel junctions, which you can see in the blue region. Figure C is the schematic representation of the X-bond qubit. Researchers also performed several tests to determine the characteristics of the X-bond qubit. As you can see in Figure A, the relaxation time varies with different frequencies. 5.40 gigahertz yields the longest T1. Figure B shows the Ramsey T2 star and the spin echo dephasing. They are 20 microsecond and 15 microsecond respectively. One thing to notice is that the 2 tests are performed on different X-bond qubits with different geometric parameters, and we are going to discuss how different geometric parameters affect the characteristics of the X-bond qubit. As you can see in Table 1, the researchers manufactured 6 different X1 qubits. There are 3 different parameters. X is the central line width, W is the gap width, and L is the arm length. The figure on the right shows the frequency dependence of T1 for the 6 qubits with different S and W. As you can see, there's a general trend of improving T1 with larger gap width. The improvement of T1 with increasing width is consistent with experiments on superconducting resonators. So the loss arises from the electric fields coupling with two-level systems with dipole moments. The loss also depends on the participation ratio, which depends on the electric field distribution. Widening the capacitor reduces the surface participation, which is a natural explanation for the approximately linear increase in average T1 with the width. Besides the basic characteristics of the X1 qubit, there are also several other features. There are also several other features that fascinates the researchers. So, firstly, it's about the scalability. The Martinez group manufactured a quantum processor consisting of 5 X1 qubits, as you can see in Figure A. Figure B shows a schematic of the quantum processor. There is a single readout line connecting to the 5 qubits. Each qubit is coupled to its nearest neighbor, which you can see from the oscillation between red and orange. Martinez group performed a complete set of universal logic gate operations on this quantum processor, and they found out that the average single qubit gate fidelity reached 99.92%, and a 2-qubit gate fidelity reached 99.4%. This places the X1 qubit at the fault tolerance threshold for surface code error correction. The results also demonstrate that the X1 qubit is a very high fidelity technology, and there's a very clear path towards scaling up to a large-scale fault-tolerant quantum circuit. So this resulted in the further investigation of the implementation of a surface code quantum computer. Martinez group introduced the concept of a stabilizer using 2 qubits and extended this concept of stabilizers into a 2-dimensional array of physical qubits on which they implemented surface code. As you can see in Figure A, Figure A is a 2-dimensional array implementation of the surface code. Data qubits are open circles and measurement qubits are solid circles. There are measure Z qubits colored in green and also measure X qubits colored in orange. Away from the boundaries, each data qubit consists of 4 measure qubits, and each measure qubit contacts 4 data qubits. The measure qubits perform 4 terminal measurements, which can be seen in Figure B and C. If you're interested in the topic, I recommend reading the complete paper from Martinez group in reference 7. The paper discusses the feasibility and how the surface code works in great detail. And now let's take a step back from the technical details of the X1 and talk about the comparison with other structures. So firstly, X1's, as you know, is based on the Josephson junction. X1 is a macroscopic quantum phenomenon, while other structures such as electron spins is mostly microscopic. Secondly, superconducting qubits is a more mature structure than structures like NV centers. Thirdly, as I mentioned before, the X1 qubit has a very high gate fidelity and a relatively long coherence time. And finally, the X1 qubit is very easy to scale up given its connectivity, fast control, and manufacturer requirements. Given the promising features of the X1 qubit, I believe that there are a lot of potential impacts. So the first and most obviously, the X1 qubits could lead to the implementation of an on-chip surface code quantum computer. the XPON could also become the standard qubit for future quantum processors if further tests prove promising. And lastly, it could become the benchmark for designing qubits in the future. However, there are still a lot of future work and challenges. So firstly, it is essential for the group to further collaborate with Google on the XPON qubit. Martinez group has been collaborating with Google since 2014, and as we all know, Google is an industry leader in the field of computer science. And I believe that such collaboration could lead to huge resources and talent devoted onto this topic. And second, Martinez group currently have quantum processors consisting of 5 qubit and 9 qubit. I believe that it is essential for them to scale up the number of qubits in their quantum processors and test and conduct future tests on these quantum processors. Thirdly, as I mentioned before, the XPON qubit is highly dependent on the frequency as well as the geometric parameters. I think that further investigation could be devoted into improving the spatial structure to optimize the coherence time connectivity and control. And last but not least, material defect poses a great threat to the XPON qubits. Thus, effort could be devoted into finding better fabrication technique to eliminate these defects. These are the references used in my presentation, and I am now open to any questions. Thank you very much.